All right, so I wanted to say a little bit about how much bigger the cardinality of the interval 0 to 1 is compared to the natural numbers. And we're going to do that by thinking about, we're going to compare the number, so to speak, of rational numbers compared to the irrationals. And we're going to get kind of a surprising result, sort of the theme, I guess, of the section. Now, I'm going to do this is not at all a rigorous treatment of the topic. I just want to give you a sense for the results that come out of it. But it's not really good mathematics. Right? So this is going to be a very hand-wavy kind of like explanation. But the result is important. We just don't have time to do a course in measure theory, which is what it would take to do this rigorously. So I want to start with just a couple of observations. And again, we're not proving these things, right? We're just kind of seeing how it turns out. So first off, we know that the measure of the closed interval 0 to 1, when we say measure of an interval, what we mean is the length. And so the length of the real number interval 0 to 1 is just 1. And we also know that the interval 0 to 1 is made up of the rational numbers that are in 0, 1 together, or union, with the irrationals between 0 and 1. So all the real numbers that aren't rationals. And these sets are disjoint, right? Numbers either irrational or rational. And so what that means is the measure of the rationals, or if you want to think of it as kind of the length of the rationals, it's a little weird to think of it that way, but that's how we usually understand measure on the real line. Let's see if I can make this a little bit more legible. So the measure of the rationals in the interval plus the measure of the irrationals, again, inside the interval. But that sum has to be 1, right? The interval 0 to 1 is made up of these two disjoint sets. The length of that interval is 1, and so the measure of the two sets individually, when you add them up, has to be 1. Now, what we're going to show is the perhaps surprising result that this piece, the measure of the rationals, is actually 0. And what that means is basically every number that we've ever encountered, calculated with, put into a computer, or that a computer has dealt with, right, those are all rational numbers. As soon as you write down the decimal number of a number, you're basically writing down a rational one, right? You can do the symbol where you indicate that it repeats, but if you actually want to work with a number, you have to give a finite decimal expansion. And so this is saying that all of those numbers make up roughly 0% of the real numbers. Right? So in a certain sense, the rationals, which we are most familiar with, are roughly measure 0 compared to the numbers that we're not familiar with. So we have our experience with the rational numbers is a very limited experience with real numbers in general. All right, so one of the ways that we could show this is just by showing that whatever the measure of the rationals is inside 0, 1, it has to be smaller than any positive number. So because we've already shown the rationals are countable, I can represent them as kind of a list of points. And I'm going to kind of envision covering each point with a small line segment. So this segment, let's say, has length 0.1. This segment is smaller, has length 0.01. This segment 0.001, and so on. Now we know that individual points have length 0, And so the sum of the measure of this set of points is less than the sum of the segments that's covering it. So here, the measure of all of the listed rational points has to be less than 0.1 plus 0.01 plus point. So I would just get 0.111 and so on. But I have noticed that because points have length 0, I really overdid it with covering them with segments this long. So instead of starting with 0.1, let me be more efficient, get a better estimate, and start with 0.01, and then a 0.001, and then a really small 0.0001, and so on. Well, points have measure 0, so it's got to be less than the measure of the segments that are covering the points. And so that's less than 0.0111. But I could do this starting with as small a segment as I wish. So I could redo it and get something less than 0.00111 or less than 0.0000111. And in fact, I can arrange to cover all of the rational numbers with segments so that the total length of the segments is less than 0.0000, as many zeros as you want and then some ones. So what that means is I can make the covering of the rational points have length less than any positive number. And the only way you can have something be less than any positive number when itself is non-negative is if you get 0. So this sort of hand-wavy argument is showing that the only sensible way to define the measure of the rationals inside 0, 1 is 0. So kind of as a probabilistic interpretation, if you were to randomly select a number from the number line, the chances of you getting a rational number are roughly 0. So again, this whole subject I think is really interesting, very surprising in a lot of ways, and this is one of my favorite results because almost, I know we've written down numbers like pi and square root of 2 and so on, but I mean, anytime you've ever gotten a number out of your calculator, it's been a rational number. And so to be able to show that sort of all of our numeric experience amounts to roughly 0% of all the reals, I think is an interesting result. This argument will not be requested of you on an exam. I just wanted to show it to you.